Now we shall be looking towards that how to find the magnetic field at the axis within current carrying solenoid. Right? Now as we know that solenoids basically they have a number of turns. Right? Like for example, this is the case of a solenoid. Right? And over here, the axis is meant about this line which is passing basically through the center of the solenoid. Now, to find out at any point the magnitude of this magnetic field, let us first of all take that this is, say, dx. We are taking a small amount of this solenoid, right? And over here it is stated that n is equals to number of turns per unit length. Right? Then obviously for dx meter or dx length, the number of turns, that is capital N for dx, will be equals to n, or the number of turns per unit length, multiplied by the length what we actually are taking into account. This is dx. Right? So for this small, like this section, let us make the diagram. Let's say for example, this is the top portion of the solenoid and this is the lower portion of the solenoid, which means that the solenoid is like this. Right? And the axis is meant as such it would pass from the center. Right? Now over here we are taking dx. So let us check that dx starts from this point. This is a magnified view of this solenoid. So it turns, it's like it is from over here, this point, it is starting and it is ending, the dx is ending at this particular point. So this will basically be dx, right? Now, if we draw these lines likewise, obviously what this line will show? This line will mean the radius of each coil, right? So let the radius of each coil be represented by R. And we wish to find out the B at this particular point. Right? So, we could say that first of all, it would come like this for this point over here and likewise. So this point will be somewhat over here. We wish to find out the magnetic field at this point. Now let us term this point as A, this as B, this as, say for example, P, and from this point we wish to draw the perpendicular on this line. So this is perpendicular, right? And the length of AP, as we have seen, for like there was a coil, right? And we say, for example, it is only a coil over here. Forget about this parts, right? This is a coil, and this is the axis, and this is the point on the axis. So if we could memorize from previous lecture, it is actually stemming that topic. So over here, let us check the length of AP as equals to, say, A. And if we put this point as C, then the length of CP, let us put it as is equals to X. So this CP entire length will be X, and this AP will equals to be, say, A. Now, since GL is acting a small region over here, so the DL will act likewise, right? And the distance from this point to the point where we actually intend to find out the magnetic field is in this direction. So, as we know that the angle could be considered will be this. This one is equals to theta. And likewise, this is the dtheta, because if this is theta, then a slight change of the angle will mean a slight change over here, right? Because we are taking the DL for over here, and now if dx comes to like this, then it will seem that a small angle change actually happened, right? So this will be d theta. Now over here, let us take this point as, say, N. By the laws of geometry and trigonometry, we can state that Bn over here is equals to A d theta. Right? Now, let us check only one loop over here. Now, if this is only a single loop, at that time, on the axis, which is separated, this one, what a distance of, say, x, what can it be? We know that over here, the B was found out to be mu naught multiplied by R multiplied by this one is, say, A, and this one is R. So I R square divided by 2 multiplied by R square plus X square to the power 3 by 2. We have seen it in the previous lecture, taking the instance that there is only one coil, and we had found out that what would be the magnetic field intensity at a point on the axis separated by a distance of x from the center of the plane of this axis. Okay. Now, the main difference of the solenoid and in the previous case is that there was only one turn, and now we could see that there would be many more turns like this. We had found out only for one turn, but in this value of dx, or within the range of dx, there would be many more turns, right? And as I told, that simply we need to multiply by the number of turns, then only we will find out that what is the real value of B for a given number of turns. So just we need to multiply it by the number of turns, and as we could see over here that the number of turns is equals to n multiplied by dx, where n is the number of turns per unit length. So we can write over here as n multiplied by dx. Now we are taking this for a small interval of dx. This is a small interval of dx, right? There are also other lengths which will affect at that point. Say for example, there might be a point from over here to over here at this interval which will also affect this. There might be some dx at this point which will also affect this. So whatever now b we are getting, that is only for a small part, that is dx. So we can write it as db. Right? Now from trigonometry, like we could find out that from triangle ACP, right? If this angle is theta, then obviously these two lines are parallel lines. So this angle will also be equals to theta, right? So we can say that sine theta is equals to r square divided by, it will be r divided by a. Sine theta will be equals to r divided by a. First of all, we can write this. The second is that what we can write is, over here see, there is also another small triangle. Let us say for example this small triangle. This is the theta over here. So we can take the sine theta over here as equals to this bn, right, divided by this will be the hypotenuse gx. So in the small triangle of A and B, we have found it out from the triangle ACP. Now from the small triangle of A and B, where angle A and B is equals to 90 degrees, we can apply the laws of trigonometry at A and B, and we could get the value of sine theta as equals to Bn divided by, this one is Bn, divided by this AB. Now, as we have seen that the value of Bn is equals to AD theta, so we can write over here as AD theta divided by the value of AB. What is AB? This is simply equal to dx. Is dx. So we can write that B like x, if it is cross multiplied, will be equals to AD theta divided by sine theta. Right? Now what we could do is that we could replace this value of dx with this term, right? And in this triangle ACP, also observe, in triangle ACP, if the Pythagoras theorem is applied, we could see that r square plus x square will basically be equals to a square, right? So we do see that r square plus x square is equals to a square. Now we can also replace this term of r square plus x square as a square, right? So we can write this term as mu naught I r square multiplied by this gx will be now replaced by a d theta divided by 2. What is r square plus x square? It is a square to the power 3 by 2, and this was dx was equals to ab theta divided by sine theta. So we need to put the sine theta over here. Right? Now, what we can observe is this could be equated as dB will be equal to mu naught I multiplied by A multiplied by d theta divided by 2. This will be a square to the power 3 by 2. It will simply turn out to be a cube, right? From the laws of indices, multiplied by a cube sine theta, and this will be multiplied by r square. This one r square, right? So we can see that a will cancel out this a cube, leaving only a square in the denominator side, which in turn the expression now will start looking as mu naught I multiplied by d theta divided by 2 sine theta. This is mu naught we have put I, then d theta, leaving only the r square. Now 2, the sine theta, leaving the a square. Now observe that this is r divided by a square, what we can write, because over here in the numerator this is r square and on the denominator this is a square. So obviously we can write it as r divided by a whole square. Now what is r divided by a? R divided by a, this is basically equals to sine theta. So we can write the next expression reducing as this will be equals to mu naught I multiplied by d theta divided by 2 sine theta multiplied by this will be sine square theta, or sine theta to the power 2. Now again observe that this is sine theta, this is sine theta to the power 2. It can cancel out, leaving only sine theta in the numerator, right? And this everything which we are doing is dB. Now we need to find out the actual B at this point P for the entire solenoid. Say for example, in this particular case, it starts from this point. So we are going to draw a line from over here to P. And it ends up over here, so we will draw another line that ends up at the ending point. So we could find out that, say for example, this is making an angle of phi 1, and say for example, this entire one this angle as phi 2. So now whatever the dV we will get right from starting over here up till over here, we need to integrate it. That means we are basically now going to integrate it from phi 1 to phi 2. So we can say that the total B now will be equals to the integration of dV. The integration of dV means this one. Over here mu naught is constant, I is constant, 2 is constant. It shall come outside, only the value of sine theta will vary with respect to dtheta. So we can write it as mu naught I divided by 2, and this will be the integration from phi 1 to phi 2 of sine theta d theta. Right? Now, from the laws of integration, we know that the integration of sine x with respect to dx, it actually gives us the value of minus cos x. So now we can write that v will be equals to half mu naught I, right? Okay, now let us see over here. Actually, there was a n and we missed out term on every occasion, so it could be multiplied by n. Over here we multiplied by n, again we multiply it by n. This is multiplied by n again, and n as being the constant, it will come outside. So this is multiplied by n and multiplied by n over here again, right? Because this was the n which we missed out on each and every occasion. Now this will be minus of cos theta from phi 1 to phi 2. Now since this is the negative, we could make it positive just by altering the boundary adjustment. Like the lower boundary adjustment will now come to be phi 2 and the upper boundary limit will come as phi 1. Then only this could be made positive. Otherwise, we could go by the simple laws, or the final thing will come out like to be b will be equals to 1 by 2 mu naught ni, right, multiplied by cos of phi 1 minus cos of phi 2. So this is the basic expression for the magnetic field which is experienced at any point, given the point is on the axis within the current carrying solenoid.